Hello interwebs, welcome to Let's Fix Computers. I've got an A1466 here, it's a MacBook Air, circa like 2014 to 2017, I think the A1466 is. I love fixing these things because they're cheap, they're simple, they're well documented, and they're everywhere. So I figured this would be a good way to start off the new year. So let me just grab a charger, or actually I think I've already got one plugged in, I have, and we'll connect it up and see what it does. Customer tells me that they have an orange light on the charger, but it doesn't turn on. So let's plug in my charger and see what we get. So we'll bring up the Paul Daniels meter, and I shall plug it in. And so we're getting some weird little pulses there. You can see that we're sitting at around sort of 35 milliamps, and then there was a couple of pulses up to like 100 milliamps, maybe a little bit higher at one point, but now it's just fallen off and it's just sitting at 35-ish. So it's not doing a whole lot of anything. There's someone at home there. It tried to do something, decided it couldn't, and stopped. So let's get the back cover off and see what's inside. So if we punch in a little bit closer on the logic board here, you can see there's some little sort of corrosion-y patches around here. There's some down here. And I'm going to keep, there's a little bit there as well. Anything further along? Not that I'm seeing. So this, in a recent laptop, the last MacBook Air I did actually, I mentioned about water damage caused by condensation and humidity and stuff like that. This has got that same vibe to it. This doesn't look like it's had... Well, actually, you know what? That water sensor is darkened, but again, if we look at the dust pattern, if there had actually been a flood here, I think we'd see some kind of tidal mark. You know, there's something there that kind of looks like it might be a tide mark, but this is on the other side. Remember, this flips over, but the actual dust on the inside here, this doesn't look like there's been any meaningful liquid ingress here. So, you know, I don't think this has been flooded. So again, this looks like just high humidity and damp and stuff like that that's caused this kind of damage. Either way, we've found liquid damage. That means the logic board has to come out. Because we don't know what's on the other side of it. So let's keep disassembling. I'm going to pull the logic board out. Right, under the logic board we're seeing some tide marks here. That looks a lot more like there's actually been actual standing liquid here. So I haven't turned the board over yet, but I'm beginning to think that this thing has actually seen a spill. Whoa! Yeah. Little bits here and there. I think this might have had an old spill at some point. So we've got some kind of residue there. And we've got another little bit of corrosion there. Again, we've still got honest dust along the back. A little bit... No, it's not really sticky. That's honest dust. So a tiny little bit of corrosion up there as well. I think this probably had a mild spill at some point in the past that it's probably survived, and it's just had lingering issues that have caught up with it now. So let's see what we can do. So there's a very good chance, there's nothing that stands out to me as really horrifying. It's just a lot of small little bits here and there and everywhere that I'm like, that might be it, you know. Like, for example, this chip down here has got a little bit of corrosion on it. This guy is the SMC reset area. If this chip isn't running properly, the SMC will be stuck in a reset state, which prevents the laptop from turning on. Bam, just straight away. And this guy is right at the back of the laptop. So any liquid that goes through the back of the laptop will immediately corrode this and kill the board. Because design. So that's an example on how this can happen. This guy here, I'm fairly certain that's the PP Bus G3 hot main MOSFET, and that's got corrosion around it, so that could be upsetting the main power rail. Same with these guys down here. That's critical power stuff as well. This stuff up here is backlight related, so that could be causing a short to ground that would pull PP bus G3 hot down. You know, I could keep going here. Let's see, where was that little bit of... Yeah, that guy, not sure what that guy is off the top of my head. I think that is all sys power good though. It's in the area of all sys power good, so again, that's P-good circuitry. That could prevent the laptop from turning on. Don't know what this stuff is doing. Looks important. Don't know. So, I could just toothbrush this laptop, this board clean, and that might make it come good. But I think what might be fun, I think how I'm going to approach this as a video is we're going to open the schematics for this. We're going to have a look at each of these areas and see what each of those chips are doing and how that might affect the laptop with having corrosion on it. So let's open up the schematics and we're going to go over the board bit by bit, look at each of those areas, then I'll clean the whole board up and we'll just see if it comes good, because it probably will. But I think we could learn more by seeing why that tiny little bit of corrosion here, there and everywhere, each one of those could on its own be stopping this board from turning on. So this board is an 820-00165 and I've got the schematics open in Flex Board View here. And so we're going to start up in the top left of the board here. So this is the display connector and this is the backlight power circuit here. And if we have a look under the microscope, as you can see, this is where some of our first corrosion starts. So let's take a look at what is corroded and what that is actually doing. And the two components that we care about here is Q7706 and F7700. So F7700, that is the backlight fuse. So this connects the backlight power to PP bus G3 hot. So you can see we've got PP bus G3 hot at the top and we've got backlight power at the bottom that then goes into Q7706. So PP bus G3 hot is always hot. That's what hot means. It means it's always on. So long as the battery or the charger is connected to the laptop, this rail is up. This makes it extremely susceptible to liquid damage because the way that this corrosion forms is that when you have two electrodes, a positive and a negative, surrounded by liquid, the electricity will break down the liquid into components. So you'll get hydrogen gas and whatever the other thing is. Plus the important thing is all of the minerals will drop out of the liquid and deposit on your electrodes. That's the corrosion. This stuff here, all of this chalky stuff, this is minerals and schmutz that is in whatever was spilled on it. This is why like sugary drinks and stuff like that are awful, because all the sugar falls out of it and gunks up the board. And in addition to that, it's this stuff that makes the liquid actually conductive. Pure water is non-conductive. So if you were to spill actual like pure distilled water, not a huge amount would actually happen. However, pretty much all water is going to have some minerals in it that are conductive, and that drops out, it forms this corrosion, and you have a permanent short circuit through the corrosion. So if we have a look in here, I'll put my black probe on a screw hole for ground, or just on one of the USB ports, and I'm just gonna and with my multimeter in resistance mode, let's just probe the top of the fuse. So that's PP bus G3 hot. And we're getting high resistance there. So it started off low. That was just like capacitors and stuff charging up off of the multimeter. But now we're seeing high resistance there. So our main rail is not shorted. So the lower connection there, what do we see there? We'll just try and get through there. We're seeing that same high resistance. So even though this is all messed up, it doesn't look like there's actually a problem here. What about Q7706? What does this actually do? I'll right click on it and hit search, and that automatically finds it in the schematic for me. If you're using the free version of Flex Board View, you can just Control F in your PDF. So if we go over here, this brings us down to this brings us down to page 56, which is the LCD and keyboard backlight driver. There's the keyboard down there. Don't really care about that. This is the one that we care about. This is our LCD. This is our LCD backlight. And this is a DC-DC boost circuit. So it takes a low voltage input from the main power rail and it boosts it up to a high voltage output. In this case, it can output at up to 50 volts at the output here. I have a video in my old board repair basics series that explains how a DC-DC boost circuit works, but I'm going to renew it at some point soon, so either check out the old one or make sure you're subscribed and you can find out when I do another video on this in the future. It's quite interesting, it's a cool circuit. Anyway, so Q7706 is a enabling MOSFET, so it allows power to go through it to the backlight power rail. And this MOSFET is controlled by this voltage divider here. We need the voltage at the gate to be at a specific voltage that is dictated by this resistor divider. If the voltage is wrong, then the gate won't activate and power will not flow. So in order for this resistor divider to work, it has to go down to ground. Along its path down to ground, we've got another two MOSFETs here built into Q7707. That's the smaller chip to the left of Q7706. And these have got two enable circuits, a backlight enable and a backlight reset. So if either of these signals are low, then one or both of these MOSFETs will not turn on, thus preventing our path to ground and meaning that this resistor divider will not divide and will not turn on the MOSFET. Whereas while these are high, they hold these MOSFETs on, which means we have a path down to ground, which means the resistor divider sets the voltage at the gate, thus turning on Q7706. So again, because we've got PP bus G3 hot here, we always have power at pins 4 and 3. And that's why this is a classic place for corrosion to form. But by the looks of things, there's not actually any problems here. And in any case, because we don't have a short on PP bus G3 hot, this is not going to prevent the laptop from turning on. If we get the laptop to turn on but we have no backlight, there might be additional problems here. But this is not really going to stop us from switching on. So let's move on to the next area. So next up we have this guy, and this is our SMC reset circuit. If I zoom down onto this on the schematic, it's U5510. And if we right click on that and search for it, we can bring it up on the schematic. And you can see this is our SMC reset supervisor and AV ref supply. So the important thing is that this guy is spitting out a signal called SMC reset L. That means if this signal is low, or L, then the SMC is in reset. So we need this signal to be high in order to switch on. Otherwise the SMC is held in a reset state, which is not ready. So firstly, this guy needs power from PP3V42, and it also has a couple of input signals. We've got LSOC reset and SMC on-off L as well, and these signals tell it to turn on or off. So the important thing is that we need this line to be high. So what we want to know is this shorted or is there something that might pull it low? So let's have a look at the chip and see if there's actually a problem here. So we need pin 5, and pin 5 is the bottom right there. So let's measure that pin and just see if that is sitting in a low state. That has high resistance, so the output isn't shorted. So most of the gunge is on the left-hand side, which is probably our inputs. So the top left pin is our power pin. That's PP3V42. So let's just check if that is pulled down to ground at all. And it's not. So what I'm going to do is I'm going to plug power into this board and we'll just actually see if this thing is actually functioning. So I've plugged the charger into the board and I'm switching over to voltage measurements now because we've got power on the board. So firstly, let's check if this chip is receiving power. Yeah, that looks like that's getting power. No problem. Okay, is it spitting out its signal? So let's check that bottom right pin again. And yeah, that's spitting out 3.4-ish volts. So we are getting that SMC reset signal. That is present and correct. So once again, this guy is corroded, but it's spitting out the signal that we're expecting to see, which means it's not the problem here. So the point I'm making with all of this is just because there's corrosion there, that doesn't mean that that's your fault site. By all means, we should absolutely clear that up. But that just goes to show that cleaning this up isn't actually going to do anything to help us, because this chip is actually still doing its job. So let's move on to the next area. So our next area is here, just above Q7130. So this guy here is our, this is the battery charger actually, I think. So let's right click on that and search for it. Yeah, and this is our main dual MOSFET package, which feeds into PPBus G3 Hot. So this guy basically creates the main power rail. This is a buck converter. So it takes a high voltage input from the adapter, from the charger, goes through all of this nonsense, goes through current sensing, blah, 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 and we come down to this dual MOSFET package. We have a high side MOSFET and a low side MOSFET. The high side connects to the power input, the low side connects down to ground. And this controller chip is going to switch on these MOSFETs in sequence, allowing pulses of voltage through. And those pulses of voltage will hit this big inductor here, L7130, and that inductor will resist the change in current, and it will smooth those pulses into a steadier wave. And then we've got a bunch of capacitors here that's further smooth the output until we get a nice steady voltage output on PPBus G3 Hot, which should be around about 8.6 volts on a MacBook Air. So there's a little bit of corrosion around on this guy. It doesn't look particularly bad to me, but, you know, let's measure it and let's see if this guy's doing its job. So once again, I've plugged in the charger and I'm going to measure the voltage at the output for this guy. So the output for this guy is pin 10, which is actually the bottom pin, the bottom pad of this package. So it's actually under the chip. And that tallies because you can see here that we've got a big pad that goes underneath the chip. So let's just measure that pin there. And we've got 8.6 volts there. So yeah, this guy's doing his job. So we've got a little bit of corrosion around it, but that's not causing a problem. On to the next thing. Our next area is pretty close by. It's just a little bit further down to the bottom right. And it's next to Q7180 and C7184. We've got a little bit of corrosion on this capacitor and just around this MOSFET package. So what is Q7180? So we're on the same area. This is also part of the PPBus G3 Hot power supply. This is our inrush limiter package. So this dual MOSFET package, it does two purposes. It functions as a digital switch that allows the system to switch the incoming power supply on and off. And it also just regulates how fast power can flow into the system, hence why it's called an inrush limiter. The small capacitor next to it that's messed up, which one was that? That was C7184. So C7184, where are you? It's there. Now, we don't even need to bother doing measurements here because we already know that we have output here. The output to PPBus G3 Hot is already on and working, which means, again, even though we have some corrosion around this area and this area, these things are still doing their job. So there actually is no problem here. So once again, we can just ignore this. So that's the top of the board accounted for. All of those little bits of corrosion that we found when we first took off the cover, none of them are actually stopping the laptop from turning on, which is probably why it's lasted this long. This is why you can have a liquid spill that causes damage but doesn't actually break the laptop. You'll get corrosion and stuff like that, but if it's not actually causing a short circuit to any critical areas, the device will continue to work. So what is preventing this laptop from turning on? Let's flip over to the bottom. There are a couple more spots that we've got to cover, and then if we don't get any hits down here, we'll actually start going through the diagnostic routine of we don't know why this doesn't turn on. So Looking at the bottom, I'm going to start all the way over in the corner on the left here again with this guy here, U4650. So U4650, this connects into the USB port and is the Mojo Debug Mux. So what this guy here does is it piggybacks into the USB port, which is this guy over here. And what happens is if you take this laptop into an Apple shop, they'll plug a USB cable into the side of it and magically be able to diagnose all kinds of faults with the laptop using a very special machine that no one but Steve Jobs owns. And this chip is what makes that possible. What this guy does is when you plug in that special USB machine, it activates this chip, which reroutes the USB data pins into SMC debug ports. So it basically gives them a direct line to the SMC, which tells them what's happened to the laptop, assuming the SMC is able to turn on, of course. So if this guy were to have problems, that might cause our USB port not to work, but I can't see a world where this is going to prevent the laptop from turning on. If you're having issues where your SMC won't turn on for some reason or other, maybe it's getting upset by this chip shorting these SMC debug lines or something like that. But again, I can't see a world where this guy is actually causing any meaningful problems. And in addition to that, if we have a look at any major connections it has, it's powered by PP3V42, but we already know that that line works because we measured it earlier on at SMC reset. So at this point, we've no reason to believe that even if this guy is broken and not working, there's no reason to believe that it could prevent the laptop from turning on. At worst, this might prevent the USB port from working. For example, it might be stuck in the on configuration where the USB lines are just constantly running through to SMC, which means the USB port doesn't function as a USB port. But considering the laptop doesn't power on, we really don't care about USB right now. So let's move on to the next item. Now this looks fun. This is previous rework. This board has been repaired before. That's not a sticky residue or a skid mark, which is what I thought it was when I first looked. That is conformal coating. And if you look, there's actually a tiny jumper wire that's been soldered onto the board there. Wow, my probe is really bent. I should probably get a new one. Anyway, that's a tiny jumper wire that's been soldered on. And you can see where there's some exposed copper here. This area has been wicked flat, and solder rework and wicking has just damaged the surface of the board slightly, which is fine. There's no corrosion here. However, this is an existing repair, so we should entertain the possibility that this repair has failed. Now, let's have a look at what this chip does so we can see if that could be causing a problem. So, right now we are on the back of the board and we are looking at U1950. So let's search that up. What do you do? What is U1950? So, as I mentioned earlier on in the video, this is part of the Power OK generation. So in this general region of the motherboard, we are looking at P-good circuitry. So P-good means power good. Power OK or P-good circuits, their responsibility is to check if the voltage regulators have all switched on, turned on, and are ready to go. Each voltage regulator will spit out a power good signal, and the Power OK generation will take all of those signals, put them all together, and go, is everyone switched on? Okay, start the CPU. And so if any of those are missing, then we do not get that OK signal and the board doesn't turn on. So a problem with the P-good circuitry will definitely cause us to not turn on. This could be our problem. Okay, I completely botched the reading of this schematic while I was recording, so we're doing it in post, everyone. So U1950 here, this is a dual AND gate package. It's got two AND gates that take two inputs each, and if A and B are both true, then Y is high. So the chip itself is powered from PP3V42 up here in the top left, and we know that that is good already. So that comes down here. So then this first gate it's going to take all sys power good, which comes from a previous section of the power good circuitry, and it's going to combine it with PP3V3SO. So if this rail is up and all sys power good is high, then PMSOP good goes high. There is some other stuff over to the left here. We've got these CPU VR signals here. However, this resistor is no stuff. It's not on the board. That means that there is no connection between these two, so we don't care about any of this. The two signals that matter are PP3V3SO and all-sys power good. So if we come along here and we now have PMSOP good, that becomes our A signal, and that is combined with SMC delayed power good coming in down the bottom here. So if that signal is also high, then we get two outputs. We'll have sys power OK underscore R, which then becomes PM PCH sys power OK, which is our all power is OK signal. And then it also pulls up PM PCH power OK, which is another signal up here as an output. So as you can see, that's got an out flag on it. So this chip as a whole is taking a couple of previous signals, making sure that all of those signals are present, and then outputting another signal to say to the PCH, yes, all the power is okay. So let's take a look at this guy and see if it's actually spitting out its signal. So this is coming out at pin 3 of U1950. Let's measure that and see if the signal exists. After I turn on my multimeter again. So firstly, if we take a look at the previous repair that was done here, it looks like there was corrosion around pin 8 of U1950, and a little jumper wire has been put up there. So pin 8 is PP3V42, so that's the power going into this chip. And also, it looks like there's supposed to be a capacitor C1950 just above it, and I don't see that capacitor on the board, so it might have been omitted. Is that capacitor even supposed to be there? Let's quickly check. So yeah, this is a bypass capacitor. It is not marked as no stuff, so it should be present on the board, and it's not. So whoever did this repair didn't put this on the board. It's a 100 nanofarad capacitor, which isn't very big, but you know, its absence might be enough to upset this chip. I'm not sure. So at pin 3 down here, we should see a power OK signal. And we don't. So this doesn't mean that this is our fault, but we've now started to find reasons why this laptop isn't turning on. It's not spitting out a sys power OK signal. Is this chip even getting power? Because of the conformal coating here, it's difficult to get down and see if the chip is actually powering up. But we could probe some of the other pins. So I'm going to check pin 2, see if there's anyone there. No. Pin 1 is all sys power good. Anyone there? I'll just check this nearby resistor. No. So we're not getting all sys power good, which means we've got a problem upstream from here anyway. Are we able to, if I probe that one, is there any power here? Yeah, there we go. This chip is getting power, 3.42 volts coming in. So this chip is powering on, however, it's not receiving its requisite input signals anyway. So although it's got a repair on it, at this point we've no reason to believe that repair has failed because it's not getting the input signals from this area over here. So we're going to come back to that in a moment, but we have found a legitimate reason why this board isn't powering up now. So let's check our other areas, then we're going to come back to this one. So our last couple of spots are in the top right and middle right of the board. We've got a spot here around C8146. Let's just see what this guy does. 1.5 volt codec enable. Odd power enable. So this signal is an enable signal. The giveaway is audio enable. So this signal needs to go high in order to switch on the sound card on the laptop. We don't care about this. The laptop doesn't turn on. We don't care about audio. Let's move on. And finally, we have a spot here at U7320. As you can see, we've got a bit of an angry looking spot here. So what does U7320 do? Phase 2, oh boy, hello. So this is a PWM chip controlling CPU vCore. So this guy's mission critical. If this guy doesn't work, we don't get CPU power. No CPU power means no startup. So this could also be our issue. Now, I don't think this could be causing a problem, but it's not the problem that's holding us up right now. Now, if you remember when we were looking at the previous angry area, remember how, well, let's go back to it. We don't have all-sys power good, so we don't care about this signal yet because the rest of the system has not powered up. So this might cause us an issue at some point during the repair. However, it's not our main issue right now because we're missing another signal that needs to be present first. So the lack of all-sys power good, that's really what we care about at this point. So we've gone over both sides of this board now, and we found a couple of areas that are not causing a problem. We found a couple of areas that might be causing a problem, but we haven't found anything that's really a smoking gun. What we found is that we're missing all-sys power good, but that doesn't really tell us a lot. That tells us that there is a problem with the power system on the laptop, but it doesn't tell us which power system or why. So we've got a couple of choices at this point. What I could do is I could go over this board with a toothbrush and clean up any of those sketchy areas and just see if it turns on. Or we could actually start going through the diagnostic process and figure out exactly why it won't turn on. So I'm going to do one and then the other, I think. And there's a bit of a risk involved in this as far as the video is concerned, because if I toothbrush up these areas and then the board just switches on, then we'll have a victory, but we won't really know why, because, as I say, none of those areas really jump out to me as this is the reason why the board doesn't turn on. However, so that will be a bit of a boring end to this video. However, also we've learned a lot by looking at all of these areas anyway, and it also shows the value that sometimes if you toothbrush everything, or if you just lob it in an ultrasonic cleaner, which is a very fancy toothbrush, then you might just get lucky and you might not actually have to do any work. And there's a lot of value in that. So I'm going to toothbrush these areas and just see what happens. My guess is that it's not going to work and we're going to have to start going through the startup sequence of this board. So let's clean up this board and let's roll those dice. I'm just squirting a little bit of isopropyl alcohol here, and I'm just using a toothbrush to just brush the corrosion away, leaving a nice clean finish behind. It's worth noting that I strongly advise taking pictures of any areas where there were corrosion before, or just taking a note of what areas you looked at, because that might be important later on. If you're completely stuck with no clues, having areas that were corroded may be the only clues you've got. Now, we've gone over all of those clues already, so I don't think that's really going to matter, but it doesn't cost anything to keep a note of what you've already learned. All right. Brushy is complete. Let's see if anything has changed. That looks like a no. We're not seeing any of those weird pulses that we had when we initially plugged it in at the start, but also I haven't been paying attention to the other times where I've been connecting and disconnecting it as this repair has progressed. So I don't know if that's an effect of doing the brushy or whether that's just the fact that the board has settled because it's been plugged and unplugged many times. The important thing is we're still stuck in the same previous state, which was about 35 milliamps average. So let's power it off. It's time to turn on our brains now. We need to start taking measurements. Now, because I'm sitting in front of Flex Board View and we've got the 00165, which is a very, very well documented board, we have lots of information available to us. We have to climb from an S5 state up to an S0 state. So I'm going to start off by checking the S4, S3 rails, because we're probably getting, without having any main rail shorts like no PP bus G3 hot and stuff like that, we're probably getting to S4 or S3. So let's have a look and see if those are present. If we're not getting to those, then we'll start having a look at the S5 rails. So I'm going to plug the laptop in, so it's trying to turn on. Let's have a look at the S4, S3 rails. So we want to check PP5V S4, and we can check this from the top of the board. It's generated there. I'm going to turn the board around. And we can find that on top of this row of capacitors up here. So multimeter into voltage mode. Blammo. We've got nothing there. Okay, so it looks like we don't have S4. Let's drop to S5. So let's check. So PP bus, let's go from the beginning. So PP bus G3 hot. We can check that at the fuse, which is here. That's 8.6, that's fine. Yes. So let's go straight to PP5VS5. And this is on the back of the board. So let's zoom down onto this guy. So let's check that we've got our 5-volt rail, which we do. That's present and correct. So no problem there. What about the 3-volt rail? And the chip for that one is up in the top right of the board here. There's our 3.3 volt rail. So we've got our S5 rails. Well, I would go through and check the other ones, but I know these are going to pop up on the next step anyway. So the next thing we're going to do, I'm going to jump straight to missing PM Sleep S4L. So let's check PM Sleep S4L, which is up next to the SMC here. And I'm going to drop under the microscope because this is a very small resistor that we're going to check now. And we have no PM Sleep S4L. So there's our problem. That's why it doesn't turn on. All right, so the next thing I'm going to do then is I'm going to start bashing down this list of the signals that we need for PM Sleep S4L, and let's find out which one is missing. So this video is getting long, so we're going to start going through this at top speed. Here we go. Okay, and with that, we are through all of the main issues. So we're down to one last check. So if all else fails, the next thing we do is we remove R8111. And R8111 is this guy here. And what this guy does, this is a pull-up resistor to enable the memory voltage regulator. And if we remove this and the system powers up, it won't work because the DDR won't switch on. However, it will tell us that the IMC is dead. So we're going to take that off the board and we're going to just do a check and see if that's what's happening to us here. So we need to go over to, let's see, this guy here. So hot air on. Let's jump that off the board and see if that's our issue. It's not looking good, folks. Right, I've just twisted that sideways. Let's see if our PM... The laptop hasn't turned on, so it looks like this hasn't done anything. I'm just going to check that PM Sleep S4L is still missing. Okay. Right, PM Sleep S4L has appeared. So at this point, it looks like we probably have a dead IMC. We could try changing U7400 for good measure. So what actually is this? Let's just quickly search that. So this guy is... Yeah, this is the DDR3 power supply. So we could replace this guy and see if the board switches on. Our only other option at this point is that we have a dead CPU. So we're kind of into the land of we may as well try our luck here just to see if we get lucky. Maybe we have a dead memory controller regulator. Maybe we have a dead memory power regulator. I vote we try our luck. So this is a TPS 51916. So let's just find that on the board. This is on the back of the board just below the BIOS chip. So yeah, that's this guy here, which is where we just this is where we just turned that resistor sideways. So I'm going to check my spares boards. I'm sure I've got another one of these, and we'll try swapping it out. So here is my donor board. So we're going to take this guy off. This donor board has some other bizarro fault that I can't solve. I can't remember what's wrong with it, but it's missing a BIOS chip and a clock chip, so obviously I was having a bad time up there. Right. I shall steal it. No one will know, except you guys. Don't tell anyone. Oh my god. No, still nothing. Right, that is a dead IMC in that case. So those little bits of corrosion, stuff like that, nothing to do with it. What we've discovered is the IMC, which is built into the CPU, has died. That's the internal memory controller. And we know that because if we remove the resistor that tells the memory power rails to turn on, and thus the memory controller and all the rest of it, then the CPU thinks that everything is okay. But the moment you tell it to try and switch on the memory and the DDR rails, it all falls over. So that's a dead CPU. That's game over for this guy. So big sads. That was quite a journey for a no fix, unfortunately, but sometimes it be that way. However, I hope that along the way that extraneous look into all the little bits of areas and all the ways we can check is helpful. Because also, we've seen there that sometimes you can have something that looks pretty straightforward, but by the time you actually get to it, it might actually be just something terminal. So thank you for tuning in, everyone. I will see you guys next time. Bye for now.